Welcome to our webinar on the value rating. Thank you for joining us today. So just a small note, this webinar is being recorded. All attendees are currently on mute. We will send this webinar, so you will have a copy of the recording after the presentation. If you have any sort of quality issue with the audio, please note that if you're on wired on internet connection, there's also an option to call through phone call available through the dashboard on the audio on the right side of your screen. My name is Sophie Bélanger. I'm the Global Product Manager for Camfil Power System. I will be supporting our presenters today by answering your question through the chat. So if you also look on the control panel, there is a chat box that you can use to ask questions through the webinar. I'll try to answer them live as much as possible, and we'll keep the one that comes back regularly through different presenters for the Q&A session at the end. So we'll have a 15-minute Q&A session where we'll try to address the most interesting or the most common question. No worry. If we haven't had time to answer your question during this webinar, we'll answer them by email afterwards as well, so we'll get in touch with you. To kick off this webinar, we'll have Kelvin Ross, who's Editor-in-Chief of Power Engineering International. Power Engineering International is an online and print publication focusing on the power generation industry. I'll take a few minutes to introduce us to gas turbine in the context of the energy transition. Afterwards, Hitesh Pande, who's R&D engineer within our Camfil Power System R&D group, will kick off the main topic of this webinar and present us with the value rating, what it is, how it works. Followed by that, Joshua Kohn, our R&D manager, will explain us how to use and interpret the result and give us a quick conclusion. So on that, I'll leave the stage to Kelvin for his introduction. Thank you.
Thank you, Sophie, very much, and a very good morning, afternoon or evening to you, depending on where you are, joining us from around the world today. As Sophie says, my name's Kelvin Ross, and I'm the Editor-in-Chief of Power Engineering International, which is a publication that covers all forms of power generation. And the gas turbine has and continues to be one of the hottest topics of discussion for our readers. The role of gas in the global energy transition really has come into sharp focus in recent years. And it's the flexibility of gas as a fuel that's seen it become widely regarded as an enabler, as the enabler of the energy transition, and being a true bridging fuel to a clean energy future. And of course, at the heart of this whole focus is the gas turbine. For years, it's been the backbone of the energy system for countries around the world, and it will continue to be so for many years to come. And it's interesting that the engineering and maintenance of gas turbines has very much kept pace with all of the many digital innovations of recent years. It's a certainty that all gas turbines will one day, perhaps sooner rather than later, run on clean or even green gas. However, in the meantime, what gas turbine operators around the world want to know is how to balance their energy consumption, their power output, and their sustainability in the most efficient way possible. And today we're going to focus on the vital role that filtration plays in this process. And while it's not necessarily a role that's overlooked, but it's one that I think is certainly underestimated. And over the next hour or so, you're going to see and hear highlighted an innovative new rating system for gas turbine operators that makes that output, sustainability, consumption conundrum, which is very complex, very easy for them to understand. So with that, I'd like to hand over to the first of our presenters today, which is Hitesh. Hitesh, over to you.
Thank you, Kelvin. Good day, everyone. My name is Hitesh Pande, and let's begin our webinar with a brief introduction of Camfil. Camfil is an air filtration manufacturing company, and we provide complete solutions to industries ranging from nuclear power plants, HVAC systems, all the way to the oil and gas and power generation industries. In the power generation industry, for example, close to 99% of what goes into the turbine is air. And this is why we believe at Camfil, it is critical the inlet filtration system is properly designed in conjunction with the end user to maximize performance output on the gas turbine operator side. The goal of the value rating is to create an immediate link from the filtration system to the gas turbine operator outputs. And we like to do this in an intuitive manner. By creating this link, we are also removing all the complexity regarding filtration dynamics and focusing only on the output of our customers. So let's look into what are some of the complexities on the end user side for air inlet filtration through a situational example. Imagine you are provided the two filters. With your current knowledge on air inlet filtration, please select whether the F8 ISO EPM1 70% efficiency at 130 Pascal versus an E10 ISO EPM 95% efficiency at 230 Pascal pressure drop. Which of these two filters is better? And if you're not sure, please select the I don't know option. So let's take approximately 30 seconds to reflect and provide an answer. We will review the answers of the group together once we have the replies. So thank you everyone for your feedback. We could see here approximately 13% of the audience chose the F8 filter. And that means they believe having a lower initial pressure drop outweighs the impact of having a lower filtration efficiency. We can also see close to 56% chose the E10. And that means they believe better initial filtration efficiency outweighs the effect of the higher initial pressure drop. And lastly, close to 31% of people in our audience chose the I don't know option. And this means we might be unclear of what does an F8 or an E10 filter mean. What is an initial pressure drop and initial filtration efficiency, and how does it impact the end user? So now let's go back to the presentation and explore the I don't know option in a little bit more detail. The first question is, what is an F8 or an E10 filter? And what does that mean? So an F8 and E10 represent two separate filtration classes. And without going into too much details, this means that an F8 filter, you will see more dust particles in your gas turbine compared to an E10 filter. The second point to notice is both F8 and E10 filters look exactly the same. A lot of filters look the same, feel the same, but have completely different filtration characteristics. Just by looking at the filter, it's impossible to tell them apart without a label. Point number 3 to address is, what is a total inlet pressure drop? In the filtration industry, we define inefficiencies or irreversibilities in a system by total pressure drop across the system. This means the F8 filter will be more mechanically efficient compared to the E10 filter, as it has a lower total pressure drop. So with these key components defined, let's visualize what a higher filtration efficiency really means by looking at example compressor blades after 1 year of service. This is an exaggerated example with the purpose to highlight the effect of higher filtration efficiency on the gas turbine operator side. We could immediately conclude the E10 filter will yield much cleaner compressor blades after 1 year of service. This in turn will translate to less degradation of the compressor efficiency compared to the F8 filter design. So the question is then, is this increase in compressor efficiency worth the 100 Pascal initial pressure drop cost? After 1 year of service, for example, does this conclusion still hold? These are very difficult questions to answer based off the information given on the labels of filters currently. The value rating, however, was designed to answer these types of questions. So before we go into that, let's quickly explore the filtration standards that currently exist to quantify initial pressure drop, initial filtration efficiency, and pressure drop as a function of time. So there are 3 key standards commonly used in the air filtration industry for power systems: EN 1822, EN 779, and ASHRAE 52.2. The problem with these standards is that they're localized to different regions of the world. For example, EN 779 is a European standard, whereas ASHRAE 52.2 is a USA standard. And each of these standards actually define filtration efficiently differently. For example, a filter in the USA is rated as a MERV 16. That exact same filter in Europe could potentially be 6 different filter classes. This makes comparing filters of different standards impossible. And this is why ISO 16890 was introduced, with the goal for all filters to communicate in a common language. This international standard has its positive points for a company like Camfil, where we communicate about filters on an international level. However, for our customers, this is still not relevant. No current standard helps in bridging the gap between technical filtration parameters and gas turbine operator outputs. There is, however, a rating system which bridges this gap specifically for HVAC systems, known as the EUROVENT rating. Now, there's a very specific reason why the EUROVENT rating is not adopted in the gas turbine world. And the reason is the EUROVENT rating was designed specifically for electric motors in the HVAC system. An electric motor has fewer moving components and significantly less mechanical complexity. The EUROVENT rating, so therefore the EUROVENT rating can simplify the logic behind the rating system to only take into account pressure drop of the filter. Whereas for gas turbine applications, we cannot make this simplifying assumption. We know from our previous example, filtration efficiency plays a huge role on compressor and turbine efficiency, which in turn affects the efficiency of the entire system. Moreover, we also learned pressure drop plays a critical component in the decision-making process, both initial pressure drop and loaded pressure drop of the filter. As the combination of these 3 parameters is not taken into account in the EUROVENT rating, we at Camfil Power Systems have developed the value rating, a rating specifically designed for the gas turbine world. The value rating is the simplest gas turbine specific filter rating system in the industry. It is based on a recognized international standard, and it is meant to be the most intuitive filter rating system for gas turbine operators. The goal of the rating system is to quickly differentiate filters by linking the technical characteristics of the filter to the 3 key outputs for a gas turbine operator, which we believe are power output, fuel efficiency, and sustainability in terms of carbon dioxide emissions. So at this point in the webinar, we have briefly reviewed the output from current filtration standards. We've also reviewed why the value rating is a novel rating system, specifically for the gas turbine industry, how it will help in simplifying filter selection for the end user by creating a direct link between the filter technical characteristics and the power output, fuel efficiency, and CO2 emissions of the gas turbine. Another great way to think about the value rating is as a simplified mini life cycle cost analysis. And in order to perform this analysis, we need to make assumptions regarding standardized site conditions and standardized environmental conditions. With now the high-level understanding of the value rating completed, I will pass it off to Joshua to describe in more detail how the value rating works, along with its underlying assumptions and limitations. Thank you.
Thank you, Hitesh. So now I'll take over for a few minutes and talk about how the value rating works and how to use the rating to get insights into what filters are best to use for different applications. So as Hitesh was mentioning, what we're looking to do with the value rating is make a gas turbine specific rating per filter. Instead of focusing on technical filter parameters of what is the efficiency, what is the pressure drop, we want to convert these into actual outputs. We want to convert these into rating filters based on how much power you could expect the gas turbine to make with different filters, how much fuel you could expect to burn, how much CO2 you could expect to release, and link the filter performance to the actual gas turbine performance so that you don't select a filter based on an arbitrary efficiency level at 0.4 microns. You select a filter based on how much power output you want the gas turbine to produce. So what are we including in this calculation? We are including two main parameters. We're trying to find the balance on what is the best filter to use if you look at both the amounts of gas turbine fouling you could expect to have because of the filter efficiency, where a higher and higher efficiency filter will lead to less particles entering into the turbine, less fouling, and greater gas turbine performance. But we know that that higher efficiency could sometimes come at a cost, where if the filters become too high in efficiency, as they increase in efficiency, the pressure drop of the filters could increase, and that higher pressure drop will make the turbine produce less power. The higher the pressure drop means the more energy is just used in pushing air through the filters, and the less energy is used on productive work for the gas turbine. So what we're trying to balance here is to come to one number that includes the effects for the average industrial site for a frame size engine, how much fouling you could expect to have and loss of power and turbine performance in that way, as well as how does the initial pressure drop of the filter, as well as the average dust loaded pressure drop of the filter over its life, rob that turbine of its performance. And by balancing these two together, we can come up with one number that has the combined effect on the gas turbine performance. And that's what we'll be looking at today. So Hitesh had shown what the value rating looks like, and this is what the entire label would be like on a filter box. So what we're seeing here is for any given filter at a nominal airflow, the very center of the rating is the output rating, where we have a 92.2% output rating. Now we think that power output of the turbine is quite critical. And what we're showing here is if you would run a gas turbine with one particular F8 filter with its pressure drop, both new and clean, as well as loaded with dust, then that turbine would be producing about 92.2% of its nominal rated power output on average throughout the year. And this is the combined effects of fouling, of pressure drop on the reduced engine performance. So we're giving the output rating a lot of prominence here, where that's rated at a 92.2%. And we also have a sliding scale from E all the way to A++ to try and put this number in perspective. Is 92.2% good versus the other filters on the market today, or is that subpar versus the other filters on the market today, to give you a sense of scale on where are you in your filter selection. So here we're seeing that a 92.2% output rating is just barely enough to qualify for a C-rated filter. To be a C-rated filter, you'd have to be somewhere in the 92 to 94% output rating range. And that's a far cry away from the A++ rated filters that are filters with high efficiency, low pressure drop, and long life that could deliver over 99% of the gas turbine's nominal power output throughout the year. So that's the first thing that we're looking at here. We get a sense of not filter-related parameters of what is the filter efficiency at a given particle micron size, what is the pressure drop in Pascal. We're looking directly at gas turbine specific numbers that help you make decisions from one filter to another. I'll go through the rest of the label and then we'll work out an example of how we could use this label to compare two different filters. So moving on to the next component of the label, power output isn't the only important thing for gas turbine performance. So we also show the fuel penalty. So we're showing here that with this filter, because of the effect of the filter's efficiency, because of the typical fouling that you could expect throughout a year with this filter, as well as the pressure drop of the filter, the gas turbine would be burning almost 4% more fuel per megawatt hour produced. So more technically, the heat rate would be 3.8% higher when this type of filter was used. So we could really compare right away the output rating, the amount of power output, as well as how much additional fuel you would have to burn because of this particular filter. And the last value is we're showing the CO2 savings. So we're showing it here. We're making a link between fuel consumption and CO2 outputs. Now we know that why do gas turbines produce CO2? Well, the more fuel is burnt, all of that fuel is then converted into CO2 and heat, which is used to drive some output, to spin a generator, spin a compressor. But if we could reduce the fuel consumption, we could also reduce the CO2 output of the gas turbine. So here I've switched over to showing a CamGT 3V600 E12, a highly rated E12 filter with a 99.2% output rating. And we see that this particular filter could save you almost 18,000 tons of CO2 per terawatt hour of gas turbine output. So that just gives you a sense of scale of how much less CO2 would be released with any given filter being used. So here, when we're looking at the value rating, we're seeing 3 gas turbine specific numbers that are being presented. We're not trying to rate a filter based on its efficiency. There are already a lot of filter standards to do that. We're not looking at rating a filter on its pressure drop alone. Again, many filter standards to do this. We are looking at actual turbine performance. How much power output could you expect to have if that's relevant to you? How much fuel would you expect to burn if that's relevant to you? Or how much CO2 do you think that you could save if you use one filter over another? So now that I've explained the different components of the label of what we think the most important values are that end users should use to select which filters they would run on their turbines, we'd like to ask you, what do you think? So out of these 3 different ways of rating filters, either rating them on the amount of power output you could get, or on the amount of fuel you would burn, on the amount of CO2 you would save, which, if any, of these 3 values are relevant to you? So again, we'll leave about 30 seconds for you to answer this question. And let's get a sense of scale on if any of these values are important to you or when selecting filters. Okay, so now let's take a look at the answers here. So we have a lot of answers going towards output rating, where just the amount of power output of the turbine is relevant for them. That's not unexpected here. We think that we see for a lot of end users, the reason of using a gas turbine is to get that power output. So trying to keep up as much output as you can. It's also nice to see nice amounts of people choosing the fuel penalty as being relevant to them, as well as the amount of CO2 which is outputted because of that fuel. And only see a small percentage of people going towards none of the above. So some very interesting answers here. So it does look like we're trying to narrow down on a couple values that are important for the audience here at least. So now let's take a look at how we could use this value rating to compare different filters and see what sort of outputs you could get, what sort of gas turbine outputs you could have because one filter over another. So in order to use the value rating, let's first look at a typical turbine that we'll use for our example. Here I'll be doing some math for a 125 megawatt turbine, which is being run 8,000 hours per year baseload with some nominal selling price of electricity, heat rates, and fuel cost. You could do similar math for your sites, for your fleets, for whatever you're interested in looking at, but this will just be my example I'm gonna run with for the next few minutes. So in this example here, this one turbine is going to be bringing in a revenue of $35 million per year running baseload, and it will be consuming $24 million worth of fuel. So let's keep those two numbers in mind and see how the value rating makes comparing filters quite easy. So let's first go back to the output rating. Now here we're going to be comparing two different filters, our CamGT 3B600 E12 with an output rating of 99.2%. That's getting a pretty good score, an A++. We compare that to a typical F8 rated filter that has an output rating of 92.2% for a rating of C. So here right away we get some sense of scale. We're going from a C rated filter to an A++ rated filter. We should see a pretty big difference in performance. And to get the additional outputs, to see how much additional power output you could expect to get when using the CamGT filter over the F8 filter, well, let's just subtract the output ratings one from the other. 99.2% minus 92.2% is a 7% increase. So right away we see from the output rating that for the average industrial site, based on the typical fouling we would see and the typical dust loading we'd see, you would produce 7% more power outputs using the filter on the left, the E12 filter, compared to the filter on the right, the F8 filter, even taking into account the pressure drop difference. Now 7% is a huge amount of money too. So another way of doing this is we could multiply our output rating, our 99.2%, by our $35 million expected like nominal power revenue, and we could find that with this E12 filter, we would actually expect to have $34.7 million in revenue per year once you take into account fouling and pressure drop increases, minor changes. While if you had the F8 filter, you'd only get 92.2% of that nominal power revenue. So you'd only make $32.2 million per year. So that extra 7% power per year means an extra $2.5 million in revenue yearly for this 125 megawatt turbine running baseload. So here right away, we could see how easy it is to either just compare the output rating itself, subtracting 99.2 from 92.2 and getting our 7% additional revenue, or just multiplying that 7% by the amount of power revenue we want to get, and finding out that we get an extra $2.5 million per year. So this really shows the value of switching from one filter to another in a much more concrete way, instead of just saying, well, do I want an F8 filter with 130 Pascal or an E12 filter with 200 Pascal? That's not a very easy decision to make. Now let's look at that from a fuel penalty side as well. So in this example, we could see that the CamGT 3V600, because of its pressure drop and its expected particle penetration, we're going to be burning about 0.4% more fuel during the year, compared to 3.8% more fuel during the year with that typical F8 filter, for a savings of, well, 3.8 minus 0.4, for a savings of 3.4%. So you could save almost 3.5% of your fuel consumption throughout the year by picking one filter versus another. And that comes out to a savings of about $800,000. So again, a very considerable amounts of savings. And now finally, let's look at that on a CO2 side. So the 3V600 E12, that will save you almost 18,000 tons of CO2 versus a reference M6 filter. If we used an F8 filter, we would save almost 4,000 tons versus a reference M6 filter. So to compare them one versus another, let's again just subtract them. And we find that using the CamGT E12 versus an F8 filter, we could save about 14,000 tons of CO2 per terawatt hour produced. Now, to put that into perspective, first, what is a terawatt hour? 1 terawatt hour, that's the amount of energy produced by our 125 megawatt turbine running 8,000 hours per year running baseload. So that's about the power made during 1 year. So again, we're getting about a 14,000 tons of CO2 savings throughout the year. But to figure out what does 14,000 tons mean, I think when numbers get so big, they're a little bit hard to put into perspective. Well, the average car in North America produces just under 5 tons of CO2 per year. So getting rid of saving 14,000 tons means the equivalent of taking almost 3,000 cars off the road for a year, only by upgrading the filters on one turbine from this F8 to this E12 filter. So that's an incredible amount of CO2 savings and of reduction of cars on the road equivalencies from replacing air intake filters. So let's go over this one more time and just look at the overall summary. So when we're trying to compare these two filters, the CamGT E12 filter to any other filter that you might be interested in, one way of doing that is by comparing the efficiencies per ASHRAE 522, EN 779, EN 1822, any of the filter standards, and trying to say, well, what filter class is best for me? How high should I go in efficiency before the added pressure drop of that filter starts robbing me of all the extra performance? What is the right break-even points? So one way to do that is to look over all of the filter standards that are only rating the filters themselves and try and compare. But we wanted to make that much easier here and show you the expected impacts on the turbine on these three main ways: output rating, fuel penalty, and CO2 savings. And once you have a value rating in front of you, this is very easy to do. All that you have to do is subtract one number from the other, and you could find that here, picking one filter over another would mean that you're producing 7% more output. You're burning almost 3.5% less fuel per megawatt hour produced, and you are producing 14,000 tons less CO2 per terawatt hour produced. So you could very quickly go from a technical filter comparison to a gas turbine specific value comparison to make your decisions much easier. Now here, we've used two filters with extremely different efficiency levels that really highlight the difference. But you could also use the value rating when comparing filters of the same or similar efficiency levels to try and figure out what the value differences are to you, so that you could come to better, more educated decisions on should you use a F8 versus an F9 filter? Should you use an E11 versus an E12 filter? Is spending the additional money on one filter with a slightly lower pressure drop worth it compared to another filter? And you could really break down how much you are getting, what the values are for you when comparing two filters, to make more educated decisions. And we think that the more educated decisions that you can make, the better off everyone's going to be. So we are very happy to see that there are several other filter manufacturers that are present in this webinar, and many different end users. So we'd like to make this value rating as easily accessible as possible. We don't want this value rating to only be specific to comparing Camfil products one versus another, but we think that this whole idea of looking at selecting filters not from a filter efficiency point of view, but from a gas turbine value point of view, is something which will really benefit the industry. So we'd like to make this as easily accessible as possible. And in order to do that, we've put up a website here at thevaluerating.com, where we have an online calculator where anyone could input in some key filter parameters from different third-party test reports and generate your own value rating to help compare filters from any manufacturer, or compare any manufacturer's products against Camfil products, and really to see from a neutral third-party perspective what are the actual benefits. So what we're looking at here on this calculator is we're looking to enter the model of the filter class, as well as either the filter efficiency, the ISO EPM1 min efficiency from an ISO 16890 or an ISO 29461 test report, or the minimum efficiency from a EN 1822 report if it's a higher end filter, as well as the filter efficiency, both clean and with 250 grams of ISO fine dust loading. Now, once we know all of these filter technical parameters from a third-party test report, you'll be able to generate your own value rating for any given filter and use that to compare and really make sure that you're making the right choice. I think that we all win if the gas turbine market is selecting filters for the highest efficiency, the highest outputs, the least fuel consumption, the greatest CO2 savings, and really make these selections quite easy. move on to my last slide over here. So when we're looking at some further considerations, now we really think that this value rating is a step forward for filter selections, trying to make a life cycle cost analysis generalized and put right on the filter label so that you could very quickly pick the right filter level. For years and years, we've had people come to us with questions like, well, how high should I go in efficiency before the pressure drop starts choking the turbine? Or really, what is the difference between an E10 and an F9 filter? How much performance difference could I actually expect? These are the kind of questions that are relevant to most people, and we want to be answering with this value rating. So this value rating we expect to grow over time, along with one of the new filter standards that's currently under development, called ISO 29461. Now, this ISO 29461 is going to be the first gas turbine specific filter standard that is currently in active development among many different filter manufacturers and gas turbine end users, where we're looking to see what value filters really bring to the turbines. So in addition to the value rating as presented right now, which is showing the differences in output and fuel consumption in CO2 savings, there's a couple other things that you should be looking at when selecting filters. Well, and I have a couple of different things listed out here. It's important to not just look at the typical average site, but if you want to be looking at filter life, then it's really good to narrow this in to the actual site that you're at and the actual PM2.5 dust concentrations that are present. And we have tools, Camfil has tools like the LCC Power that could help predict filter life in many different locations. It's also important to look over things like the filter strength, make sure that the filters are not going to burst over time, or if the turbine is going to be used in an offshore or coastal site where corrosion could be a concern. Then it's very important to look over salt penetration and water penetration, the performance under deluge sprays, or looking over the self-cleanability of filters. So these are all some secondary things that are very important to look at when selecting filters. And as the ISO 29461 continues to develop, we will continuously build on the value rating to include more and more of these parameters into helping select the best filters for all different types of applications. So that's about 44 minutes into our presentation. We're nearing the end of our time there, and let's move over to a Q&A section. So Sophie, do we have any questions so far?
We have a lot of questions and quite a few interesting ones. So a lot of questions are kind of turning around. How do I customize this, or what if I need to something that's a little bit more custom for my site? So if I want to know based on a different dust or based on a different engine model, are there other tools available to answer those more specific questions as well?
Yeah, that's a very good question. There definitely are. So the value rating is meant to show the average performance difference on a turbine at many different locations around the world. If you're looking to zoom into your particular site, then we have tools like LCC Power, Lifecycle Cost Power, where we could use the actual dust concentration at your sites, the actual filter stagings at your sites, and come to much more detailed and accurate calculations. So we'd be happy to run that through with you. You could contact any one of us here to do a more in-depth calculation for your exact site.
Thank you, Josh. Another question. We have somebody that asked if you could repeat shortly the CO2 example and the comparison with how many cars and how does that work? That was quite impressive, but they missed a little bit of the explanation on how do you compare that.
Sure, I'll take a moment to go back to that. So when we're looking at the actual number that's shown on the value rating, we're trying to convert the reduction in fuel consumed, where every kilogram of fuel that you burn is going to be converted into CO2, a little bit of water vapor, and some heat. So we want to reduce the amount of fuel consumed to reduce the amount of CO2 which is produced. Now, the actual number which is shown on the label, this 17,800 tons per terawatt hour, that's showing the amount of CO2 that's saved versus a benchmark M6 rated filter. Now, if we want to actually use this number, I'll come back to this slide here. Now, the first thing that we would do if we're comparing two filters is let's look at the CO2 savings numbers versus the reference M6. We're either saving 18,000 tons versus our reference filter or 4,000 tons versus our reference filter. Let's just subtract one from the other and we find a savings of 14,000 tons per terawatt hour. Now we need to see how many terawatt hours are you producing per year. Where to calculate that, just multiply your megawatts per year, 125 megawatts, multiplied by 8,000 hours per year. And that gives us our 1 million megawatts per year, or our 1,000 gigawatt hours per year, or our 1 terawatt hour per year. So if we know that we're producing on a 125 megawatt unit, 125 times 8,000, we're producing 1 terawatt hour, then that means that we're not just saving 14,000 tons of CO2 per terawatt hour, we're also saving 14,000 tons of CO2 per year. And finally, if we know that one car produces about 5 tons of CO2 per year, according to the US EPA, well, we just divide our 14,000 tons by 5, and we find that we're doing the equivalent of taking almost 3,000 cars off the road by upgrading from the F8 to the E12 filters, just from the fuel savings that we could expect and the associated CO2 savings. I hope that makes more sense. If you have any more questions about that, then really feel free to get in touch with us, and we could go over that more detailed with you.
Thank you, Joshua. Quite a few more questions as well. A lot of people are pointing out that when you have a higher efficiency filter, you typically would see a quicker loading on the filter, or the pressure drop going up quicker due to loading, because you're actually catching more particles. So one of the question here would be, does the rating takes that into consideration? In what way, and what other step could be taken to look at filter life, and how do we calculate that impact in the cost?
Yeah, so that's a really good question, and I really enjoy that question, because that comes down to the typical thing that we hear a lot of how do you select the right filter efficiency so that, or the right filters so that what you gain in filter efficiency, you don't lose in pressure drop, and you don't lose in a rapid rise of pressure drop across the filter. So balancing out those two parameters is exactly what we're trying to achieve with the value rating. So if we look here at what parameters go into the calculator, we're looking at the filter efficiency, and we're also balancing that against the new and clean pressure drop, as well as the pressure drop from a dust loading test. So we're looking to see what is the pressure drop after the filter has been loaded with 250 grams of isofine dust. We're looking to, we've picked that number to see what is the typical upstream amount of dirt that the filter could see over the course of a year, or a nice amount of dirt that the filter could see over a life. So what we're trying to calculate here is we're not just looking at the pressure drop when the filter is new and clean, but we're also comparing how quickly does that pressure drop increase as the filter is loaded with dust. So in this way, filters will be penalized if their pressure drop is too high, and also if their life is too short and their the turbine loses too much performance because that pressure drop rises quickly, then they'll be penalized in that way as well. So we're not directly looking at comparing filter life here. We're not showing anywhere in the value rating this filter will last twice as long as this other filter. What we're looking to do is we're comparing the performance of the turbine as the pressure drop increases over its use. If you'd like to compare the life of the filters, then we could look at other tools like our life cycle cost power tool, which will do a simulation of filter life and predict the filter life for the exact amount of dust present at that site, as well as for for any pre-filters that are used.
Thank you, Josh. Another quite interesting question here as well. Could you comment on staging? So we've talked about one filter stage here through the presentation. What if someone has a three-stage filter system? How should he consider this value rating and use it?
That's another very good question. So we're looking at this value rating as something to be used to rate final filters. I think that I forgot to mention that earlier. So the value rating is looking at the gas turbine specific outputs. So and the goal of any filter is always to protect whatever is behind it. So the goal of your final filter in a three-stage system is to protect the turbine, and the final filter will always give the largest contributor to the overall system efficiency. So we're looking to use that final filter and see what expected performance you would have for the turbine. The pre-filters, they also play a very critical role in protecting whatever is behind them. So if you have a three-stage system, the first stage filter will protect the second and extend its filter life. The second stage filter will protect the third stage filter and extend its filter life. And the third and final filter stage will protect what's behind it, the turbine, and try and give you the most power output possible. So that's how we see at a very general view that we want to use the value rating on the final filter alone to pick the performance of the turbine. If you'd like a more detailed view of this and you'd like to see the impact of very similar filter efficiencies, let's say that you use a highly rated F8 filter followed by a low rated F9 filter that are very similar in performance together, well, we have tools like our life cycle cost power, which I've kept coming back to, is a great simulator tool that could predict the fouling levels, the CO2 output levels, the fuel consumption levels of a turbine based on many filters in series and for the actual dust concentrations on site. So if you want to do a big comparison of many filter stages, long answer, contact Camfil and we'd be happy to do a life cycle cost evaluation for you for the entire staging. Or you could just look at the final filter stage alone and run them through the value rating as shown here.
Another quick one, you quickly went through how do we incorporate the pressure drop, the pressure drop impact of loading in the value rating. One of the questions from the audience was, where can I find the data of loading 250 gram of ISO fine? Hello?
Oh, sorry, I think I muted myself for a moment while you were speaking. So that's another good question. The the pressure drop after 250 grams of ISO fine dust, that is present in one of two ways. You could either look at an ISO 16890 report, which will give you the pressure drop versus dust loading with ISO fine dust, or you could look at the new ISO 29461, which is rating filters based on the ISO fine dust loading. So some of the earlier standards, the like EN 779 was showing the dust loading with ashray dust, but we wanted to future-proof the standard and look at both today's ISO 16890 as well as the under active developments ISO 29461. So for the future here, for the present and the future, we're looking at these two ratings and test reports according to either standard that would give you that data.
And speaking of the new rating, there was a question as, do we have an idea of when that rating, the 29461, will be available on the market or will be released?
Ooh, I don't want to predict the future too much there. The standard is under active development now, and we're making very good progress on that. But I don't want to give a date on that yet.
All right, no problem. I think that covers a lot of the question. One of the other question that came back once or twice is this value rating, can it be used for pulse filter or self-cleaning filter that work with a pulsing system?
Yeah, definitely. So this rating scheme could also be used with pulse filters in order to look at the efficiency of the filters compared to their pressure drop during dust loading as well. So it's a good way of comparing any given filter and how much fouling you could expect with one filter versus another, or what sort of pressure rise you could expect with one filter versus another. So there's always some complications if your site has extremely large dust concentrations. Then we could always revert back to a life cycle cost power tool and do the calculations that way, because again, the value rating is trying to give one number for the average industrial site, which should be valid for 90% of sites, but there's always a couple outliers there where we're switching over to a life cycle cost power could be more interesting.
I think we have time for one last question. Could you comment, a few people were asking question about efficiency of the filter over time. So do we expect the efficiency of the filter to vary very much over its lifetime, and is that included in which way, and is that included in the value rating?
Okay, so when it comes to filter efficiency, we have a lot of experience with return filter analysis, where many end users have been sending back filters to Camfil for many years now, and we've been able to track the efficiency of filters under actual use cases at sites around the world. And one thing that we've noticed is while in lab conditions, the filter efficiency might increase from their initial values under heavy dust loading, we find that in real world applications, for the majority of sites, the filter efficiency remains pretty constant from its new, clean, and discharged filter efficiency. So that's our key parameter here. So what we're looking to do is that some filters have efficiency from two main mechanisms, from a mechanical efficiency that would remain long-term over many years of life, as well as a electrostatic efficiency that could give a very high initial efficiency, but that would dissipate away after a few weeks of use and not provide much long-term filter efficiency. So what we're looking to do here is to either input not just the ISO EPM1 efficiency, but the ISO EPM1 minimum efficiency when the filter is discharged to be able to measure the actual expected long-term performance of the filter. And then when we're looking at the EN 1822 efficiency at the most penetrating particle sizes, well, those efficiencies are always given discharged. So either way, we're looking at this long-term discharge efficiency as that's always been the efficiency that we see filters achieving over years of use. And that's the efficiency that we're using for our calculation.
Thank you very much. That's about it for the time we've had. So there's a few questions we have not had a chance to address. No worry, we will address them through email after this webinar. We'll either do it directly or have one of our local representatives contact you to finalize those questions. Note, you will also receive a link to this recording within 24 hours. And it also includes a survey link. So please give us your comment. I saw quite a few during the question Q&A. Thank you for your participation. And of course, we really, this is something new. This is something that we've done to simplify users' filter selection. So your comments are very important for further improvement of this rating as well. The other thing we wanted to mention here, what you've just listened to is part 2 of a three webinar series. The first one was on the various forms of degradation, was held about 2 weeks ago. That recording, if you missed it, is still available. Just contact us. And we'll have another one in about a month, August 25th, about the impact of the environment. So a lot of the question today where this value rating is a simplification, looks at a standardized environment. What other considerations should I have based on my environmental conditions? So we'll touch a lot more on that in the next webinar. We also want to give you a little bit of a premium or a advanced notification. On Thursday next week, we'll also have a webinar for a new product launch for our CAM GT series, for those of you that are aware of this product. So a new compact filter, new generation compact filter. We'll launch that this week, and we'll have our webinar next week on that subject. So if you're following us on social media, stay tuned for that registration link as well. Again, thank you very much to our presenter, Kelvin, Hitesh, and Joshua. Thank you all for your attention, and we look forward to see you in our next webinar.